Hello and welcome to another video. In this problem we're going to be working on longest string chain, and I will say that I misread the description for this problem like 3 times, so we're definitely going to read it and explain exactly what they want. So you're given an array of words where each word consists of lowercase characters, and word A is a predecessor of word B if we can insert exactly one letter in word A without changing the order of the other characters to make it equal to word B, and you want to give the length of the longest chain of words where it goes word that's a predecessor of another word that's a predecessor of another word, and I'll kind of show you what I mean. So here we have A that goes into BA because in order to make BA you don't have to change the order of the letters in A, you just add a B. Similarly, to make BA into BDA we just add a D, we're not changing anything. And then BDCA you add a C over here. And so that's going to be length 4. And in the second word, you have XB. Let's kind of just draw letters far apart so we can put stuff in. And then we have XBC, and we have CXBC. So you see how we're just adding a letter? We're not changing the relative position of anything. And finally, we add an F at the end here. So essentially, you need to be able to take the old word and add a letter somewhere in there to make a new word. And you don't have to maintain the order. So I think originally I was doing like a sliding window, and then I realized they don't actually need to be in the same order as your original list. Because you could see like A, and then we have BA, and then BDA, and BDCA. This one's in order, but let's look at some other ones. So XB actually comes after XBC in this input, but it's before XBC in this output. So all these words, you just have to use the words, but they can be in any order you want. And the other thing I did that was kind of a mistake is I also used DP, and I went from like one word to the other. And you can do DP, but the problem with DP is essentially what DP would look like is, first of all, you're going to want to recognize, let's say you do DP, I'll just briefly talk about it. You're going to look for a predecessor and then all the words after it. So you're going to want to sort this according to the word's length, and we're going to want to do that for both solutions. So actually, let's just take this one. So this is actually already sorted by length, but let's say for this one's not. So first you want to sort the letters or the words by length, and I'll kind of show you why. So if we have XB, then we have XBC, then we have CXBC, and then we have PCXBC, right? And if there's a tie, it doesn't really matter in which order. And then you have PCXBCF. Essentially, so let me just briefly talk about what the DP solution would look like if you are curious. Essentially, what you do is you start at some index. So you start at a word, and then you check. So like, let's say we start here. We would check every single word. We would just go down this array, and we would check every single word with length 3. And so you would check this word, and if there were more, you would check those. And essentially, once you get to a word that's bigger than 3, you would just stop because you only care about the word that's one character bigger. And then you can just make a helper function that just checks if a word is a predecessor of another word, right? So like for this and this, you can definitely make a helper function to check if XB is a predecessor of XBC. But this turns out to be harder to do, and it's also slower. So we're actually going to talk about a better solution, but that's roughly how you do DP. You just pick an index, and then you go down and you check for every single word that actually is works, that this word is a predecessor of. And then you would just say like, okay, well, if it's a predecessor, then my output's going to be 1 plus the new index wherever I'm at, right? And you want to sort according to length. That way, you're guaranteed to be checking in the right order, right? For a word to be a predecessor of another word, it has to be smaller. But we're going to look at the other solution. And so for the other solution, what you're going to want to do is you're going to want to actually take every single word and put it in a hash map. And so let's kind of show what that's going to look like and the reasoning behind it. So essentially what we're going to do is we're going to start with this word. And instead of looking for the words that this word is a predecessor of, we're going to go the other way, and we're going to check what word is this a successor of, right? Like, is there a word that is a predecessor of this word in our hash map? So what we're going to do is we're going to take XB, for example, and we're going to say, okay, let's just take every possible word that could have been used to make XB. And it's actually pretty straightforward to do this. You can just go character by character and delete the character. So XB either had to have been made from X or B, right? It had to have been made from X or B. That's the only words that can make up XB. X and a letter, or B in a letter, because in order for a word to be a predecessor, you have to just be able to add one letter. So you would just check, like, is X in our hash map? And in this case, it's not. Nothing's in our hash map yet. And then is B in our hash map? And it's not either. So then what would happen is, let's just call this like result or something. Now this word would have XB, and because there was nothing in the hash map, we would just say for XB, our value of the chain is 1, because there's nothing before XB. Now let's go to XBC and kind of do a few more words just to get the idea behind this. So once again, we're going to take every single word that could have been used to make XBC, and this is relatively cheap because the length of the longest word is like 16, while the length of the array is like 1,000. So breaking this word down into every possible word is basically an O of 1 operation because they're so short. So essentially for XBC, it could have either been made from XB, or it could have been made from BC, right? You can just get rid of one of the characters, or it could have been made from, what's the other one, XC? So you would just check, is XB in our hash map? Well, yes, it is. Okay, well, what's the value of that? The value of that is 1, meaning for XBC, if we know it was made from XB with a letter, we can just take whatever the length of the chain was with XB and add 1, right? So with XB, it was 1, so then we would add 1. Now the length of the chain would be 2. And then we check for BC and XC, and those aren't in there. So for XBC, it would be 2. And this is kind of the same as like the longest increasing subsequence, or one of those that you do with DP. Is essentially the same thing. Whenever you have some kind of consecutive sequence, if you add something to the end, the length of this, if the length of this was X, this is just X plus 1, right? This whole sequence is now X plus 1. So that's essentially what we're doing. We're just looking for something that could have been used to make this, and if we find it, we take whatever that value was and add 1, because we're essentially adding this to the end of that chain. And we just take the biggest possible sequence that could have been used to make that. So we'll do a couple more. So we take XBC, now we'll take CXBC. Maybe we'll do like one more to demonstrate the point. So what are the words that could have been used to make that? So it's pretty straightforward, right? It has to be a word that's one character shorter, but it has to have 3 characters in the same order. So it's either XBC, or it's CBC, or it's CXC, or it's CBC again, technically. Right? I think you have CBC twice. Actually, no. It's CXB. Yeah. Okay, so these are the words. So you would just check, like, is XBC in here? Yes, it is. It's length 2. So then if that's length 2, that means this chain could be 3. And then you would check for all the other words and you wouldn't find them, right? You'd look for CBC, XCC, and CXB. So this would be length 3, and then so on. And then you would, you would take your next word, PCXBC, same kind of thing, every word that can be used to make it. And then you'd get a 4 here because CXBC is in here, and it can be used to make it. And then you have PCXBCF, and you'd find this word in the hash map because this word is used to make it, and then you would add 1 again. And then finally, you can do one of two things. You can either just return the largest value in the hash map, right? That's totally fine. Or you could just, every time you get a value for one of these, just keep comparing it to some local maximum that you use. And that's what I'll do in this case, but either one's fine. So just to repeat myself, essentially you want to sort the words by length. And then for every single word, you just want to break it down into every single predecessor that it could have had. Check for that predecessor in the chain. And then if it does exist, you take whatever value that was and add 1, because you're essentially taking, all the values up to the predecessor. Let's call that P. And then you would just add the successor right after that. So if this is length X, this is length X plus 1. Right? This whole thing is length X plus 1. You're just adding it onto the end. And that's pretty much how you do it. And this is a lot simpler than DP. It's a lot more intuitive, and it's actually faster. So there are other ways to do it, but I think this is like one of the better ones. And there's I think there are more complicated ways. There's actually a ton of ways to solve this problem, I think. Well, let's code up this one. So essentially we're going to have a hash map, right, of like our chains. So we can call that like chains or something. And we're going to make a dictionary. And then we're going to sort the words, right? And actually, we can make this a default dict if we wanted to. And no, we don't need to do that. So we're going to sort the words. And the way to sort them by length is you can actually put in a key, and you can put in length here. And then that would sort it in ascending order. So if we actually print the words, it would go by shortest length to longest length. And it doesn't really matter. I guess it will sort them alphabetically next, but it doesn't really matter. Like, the only thing you're really concerned about is you want to get all the values for all the predecessors before you check for those in the successors. So if you had a bunch of 3-letter words, it doesn't really matter which way you process them, because for all the 3-letter words you check 2-letter words, right? And then for 4-letter words you check 3-letter words. So as long as like all the words that have the same length are done, it doesn't really matter what the order they're done in. Then we're going to have a result, right? So we can have a result, and we're going to set it equal to 1, because although technically we don't need to, we can make it 0. So now we want to actually go through every single word, starting with the smallest one. So we could say for word in words. Now we're going to have chains of the word. We're going to default it to 1, and then we're going to need to make every single word that could have been used to make this word, and get the length of that chain. And if we didn't find anything, then it would just be 1, right? Because every single word can't have a chain of 1, it can just be that word. So we're going to essentially need to make every single word. So the way to do that is you do it for I in range length word. You're essentially, all the predecessors are basically this word minus a letter. So you just kind of have like this word minus the first letter, this word minus the second letter, minus the third letter, and so on. And the way to do that, you just say predecessor equals word before the letter, whatever letter you're on, plus word after the letter, right? It should be like this. So you just add those together. Now you want to actually check if it exists. So you can say if predecessor in chains, then you want to actually get that value. So you can say chains of the current word we are on is going to be the max of what it is currently, and the chains of the predecessor plus 1, right? We're essentially just adding the word. If the predecessor chain is the biggest one, we're going to use that, and we're going to add 1. And now finally, once this word is done, we're essentially just going to maximize our result. So we can just say result equals max of the result and the chains of the current word we are on. And then that should give us the right result. And we can return the result. So let's see if we get an error before we close out of this. Oh, looks like we do. So let's see. Chains word. I misspelled. And looks like that is working. So let's just check here. So that does work, and let's submit. And you can see we get a really efficient solution here. And this is as efficient as it gets. I think for this problem, maybe you can make it a little bit more efficient, but close enough. So let's go through the time and space complexity for this one. And this one's kind of a personal preference. You can argue that since the word length is so small, maybe you can just make it O of 1, but I'll just call it like words length or something, but let's go through it essentially. So we are sorting the words. So to sort, that's going to be n log n, right? But also to, no, actually you're only, well, yeah, so here actually this might get expensive, because if the words are the same length, you're going to have to compare character by character, right? Let's say every single word is the exact same length. I think it will sort by actually comparing the characters, which can get expensive, right? So let's say you have every single word that's 16 characters, and let's say they all have the same 15 characters and so on, and the last character is different, whatever, something like that. So it's actually going to be O n log n times like the word length to sort. So now let's go through the rest of this. So for word in word, this is nothing. And then to build up each word, let's add that, and then we'll get rid of whatever the smallest thing is. So for word in words, first of all, how many words is that? That's going to be like, let's call that n, right? Now for every single one of those, we're building up a new word that is that word minus a character, which is, so essentially you're building up word length new words, and then also to actually, so this part right here is O of word length, and this part right here is also O of word length, because you're essentially building up a new string. So I think it's going to be something like word length times word length, and then the rest of it is fine. But essentially it's something like this. So I do think this will get more expensive because n is a lot bigger, right? But I guess we probably want to include all of it, because somehow, let's say word length is 16 and there's like 3 words, it can technically be smaller. So it'd be something like this, where it'd be n, and then this would be like w squared, something along those lines. Where in almost all cases this is bigger, and like I said, you can almost argue that w is pretty much constant, because it can only go up to 16, in which case you would have an n log n solution. But you could write it like this as well, because I don't think you're supposed to look at like the constraints to determine how long this is, right? You're supposed to use the variables. So, okay, now for the space. So we have a hash map, and the hash map will have all of the words as keys, right? So essentially, it can have every single word in here. So that's like WN or something, right? Like every single word will be in here, and then however many characters are in the word, something like that. If that's going to be the keys. So it's essentially going to be like the total number of letters and all of the words combined or something is going to be the space here. And as far as the values, those are going to be like O of n or something. So that part is fine. Yeah. So for every single one of these, you're going to have like one value here. So this will be like the times this, which just cancels out. So it's something along these lines. Someone can correct me if I'm wrong, but I think this is pretty reasonable. Sounds reasonable to me. Like I said, you might be able to cancel out the W, but technically, it's just small constraints. It's not good practice to do that, right? You still want to include every single variable that can change. So it'd be something like this. Yeah, I think that's going to be it, though, for this problem. So hopefully you liked it. Definitely kind of a tricky solution to do this every word possible as opposed to a DP. I think DP is doable. DP also does pass if you do want to code up a DP and a comparator for a word and its predecessor. That's totally fine. I think it's actually just harder to code, and it's a little bit slower. So I wanted to go through this one. So yeah, I guess the DP one's a little bit more intuitive, but harder to code. This one's harder to come up with, but easier to code. So trade-offs. But yeah, so if you did like this video, please like it, and please subscribe to the channel, and I'll see you in the next one. Thanks for watching.